Welcome. In this lecture, which has multiple sessions, we'll explore what we mean by constrained optimization. The main concepts for this lecture are optimization with equality constraints. What that means is that the solution has to satisfy an equation. We'll also look at optimization with inequality constraints, which is that the solution has to satisfy some inequality. In this course, we're mainly interested in convex optimization problems. A sample problem that we can keep in mind through this lecture is, suppose we're given a circular set or some other convex set, and we're given a hyperplane. Instead of asking whether a vector is on one side of a hyperplane or another, we could say, where on that hyperplane is a decision minimized? Let's take an example from linear algebra. An underdetermined linear equation is, for example, one equation with two unknowns. Here, we could say that it's the W1 and W2 variable, and that there's this single equation they have to satisfy. Well, one specific solution might be, we observe from this that if we set W1 to 0, then that means W2 has to be 2, because then 2 times 2 equals 4, and so we have one specific solution. We can also observe that if we take any scalar multiple, any real number, times any vector that is parallel to the 2, 1 vector, that if we add this to that W1, we also can solve this equation. So what that means is we have an infinite number of solutions. Now, a user might be satisfied knowing that there's a particular infinite set and that we have an equation that describes that infinite set, or the user might have some particular choice that he would like us to make. So suppose that what the user says is, what solution is closest to a given point? So here they're giving us the point W0, and what we want to do is we want to find where on the line, what point on the line is closest to this given point. So we'll refer to this as a closest approach problem with a squared length requirement. And we could set this up using that previous equation by saying any point on the line, which is we take the function and that has a scalar argument, and we insert a scalar argument, and then that will give us a vector, and the difference between that vectors that's on the line and the given point, well, we want that to be the smallest length possible, specifically the smallest squared length possible. And so this is an argmin problem, and we could set this up and we could solve this as a problem in scalar land, right? Let's also observe that there's a simple geometrical solution that we could apply. So if we were to plot this line, what we would see is here we've got the W1 is the horizontal axis and W2 is the vertical axis, and the line is this set of points in red. So any of these red points satisfies that line equation. Well, what we could then do is we could plot the given point. And now we can see that if we start at that given point and we go to a place that's perpendicular, that would be the point right here. That would be the point on the line that has the minimum possible length. Because if we were to go to some other place, then that length would be larger. So we can formulate this problem as a problem in scalar minimization, and we could formulate it as a geometrical problem. What we'll do next is we'll formulate this as a vector problem.